All right, so I'm going to talk about non-negative column selection with L1 error. Thanks, Christos, for the introduction. So this is joint work with a colleague at Google, so he's Silvio Latanzi. Okay. And so let me start with just a rough introduction to what is column subset selection. So this is one of the basic matrix problems. So we are given a matrix A, okay? And so the idea is you have a lot of columns in this matrix, and you want to approximate the column span using a very small set of columns S. Okay? So given some set of columns, you can define a reconstruction error, which is how well you can construct the rest of the matrix using just the columns that you've picked. Okay? So this is column subset selection, and usually you can ask it in any norm in some sense. Okay? So this is the aim of column selection, and your goal is usually you're given some budget on the number of vectors you're allowed to pick. Okay. And there's a lot of motivation for this. So ranging from feature selection, you want to select a subset of features, or you can think of core sets, because this is essentially approximating the whole matrix using a small number of points. And in some sense, more interestingly, you can think of this as some kind of interpretable low rank approximation. Okay, so usually in low rank approximation, you have some vectors in the span, while now you actually want to approximate the matrix using a few of its own columns. Okay, so this is a bit more interpretive. All right, so this is a very well-studied problem. Okay, so the most commonly studied thing is the L2 norm for the error here, for the recovery error. And here there are very good bicriteria algorithms. There are lower bounds as well. And there's a lot of work on this, so I've only cited a few of the early works in this thing. And one interesting fact about L2 approximation is that error using this kind of column approximation turns out to be also related to regular low rank approximation. Okay, so this is an interesting fact. Okay, so our motivation for looking at this problem was a little bit different. So we were looking in applications in which matrices were naturally, somehow they had non-negative entries. Okay, so this shows up in things like recommender systems, image reconstruction, and so on. And here it turns out that L2 error is quite unsatisfactory. Okay, especially if things are spread out. I mean, if you have a very spread out vector, it turns out in L2 norm to be really small. Okay, so just approximating it by 0 is usually quite good. So we were looking at applications with somehow L1 error was much more relevant, and entries all were non-negative. Okay, so this is the setting that we wanted to look at, but it turns out that L1 error for column selection makes it way harder. Okay, so this is a problem that people have studied. People had studied earlier and gave up on it, and more recently there were some hardness results that have been shown. Okay. And there are also some algorithms that are known, which are also somewhat bicriteria algorithms. So what they do is they get some kind of polynomial in K approximation to the error, and they use more columns than what is necessary. Okay? So this is a recent work by Song and Woodruff and others. And there's a simplification of this more recently. Okay? And so one thing I should mention about these methods is that even though they work for L1, they're essentially based on L2 methods. Okay, so they reduce the size of the matrix and apply some L2 methods. That's why you incur this poly K approximation in there. Okay. So in some sense, what we wanted to do was, can we come up with some kind of purely L1 methods that maybe are tailored towards non-negative matrices, because that's what we actually care about. Okay, so that's the motivation. Okay, so the setting we have, so in fact, we can do whatever we can even for this more general setup where you have two matrices, A and B, and you want to pick columns of one of the matrices to approximate the columns of the other. Okay, so you have the same kind of recovery error. So we have B minus the best approximation of B using columns of A. Okay. And again, the goal is the same. We want to find a set of certain size to minimize the recovery error. Okay, and as I said before, so these are, we assume that there is a good approximation where the x used is also non-negative. Okay, so in this sense, this is more like non-negative matrix factorization, if you guys are aware of this problem. So in this sense, we want, so this you can think of it as a non-zero error version of the non-negative matrix factorization. Okay, so this is the setting which we want to consider. Okay. So, and one thing you notice immediately, if I have two different matrices A and B, is the simplest version of this is when B is just a single column. Okay, and that is the sparse regression problem. This is something that is extensively studied, right? So you have a matrix A, and you want to solve Ax equals B, where X is as sparse as possible. Okay? And now we are measuring the error in the L1 norm. Okay, and these things are all non-negative. Okay, so one thing I should mention is that there's a very related problem called sparse recovery, and this is a little bit different from sparse regression. Usually in the sparse recovery problem, your focus is on X, and you really want to recover X, and you assume various special properties about A. Okay, so that's not what we are doing now. So we are just assuming A is non-negative, and you want to get an X that's as sparse as possible. Okay, so your focus is on recovering B. Okay, so that's the difference between these problems. And this sparse regression shows up in a lot of settings. So the natural obvious thing is signal compression. And another more interesting thing where non-negative entries show up is, suppose you have a distribution. Think of B as encoding a distribution of sorts. You want to express this distribution as a mixture of a small number of simple distributions. Okay? So these are settings in which especially L1 error also shows up. Okay. So this is the problem that I want to first solve, and we'll use this to solve this more general problem of column selection. Okay? So that'll be the general idea in the talk. And what we can show qualitatively are the following results. Okay? So the first thing, so this is what Christos alluded to, is that we can come up with a trade-off between error and the sparsity. Okay, so we have a scheme of getting better and better approximations while using more and more columns. Okay, so this kind of a thing is quite typical. So this is the kind of guarantee that you get using what are called Frank-Wolf type methods in optimization. Okay, so where you get better approximations using more and more columns. Okay, but unfortunately, the vanilla applications of Frank-Wolf don't hold if you have L1 error. Okay, and that's kind of one of our contributions, that we show how you get these kind of guarantees with L1 error. Okay, and then we show that, and this is what we do for sparse regression, and then we show how this leads to similar results for column selection. Okay, so those are our results qualitatively. So quantitatively, it's the following. So for sparse regression, we have the following guarantee. So suppose you have non-negative matrices A and B, and you know that there is a sparse X, so that Ax minus B has epsilon error. Okay, so I'm assuming that let's assume B is normalized to be L1 norm 1. Okay, so, and suppose there exists some k-sparse X, so that you have error which is at most epsilon. Okay. Then what you can show is that for any delta, okay, any delta bigger than 0, you can efficiently find a non-negative Y that has sparsity that depends on delta. Okay, so it's like 1 over delta squared times k. Note that there is a factor of k here, which is the optimal sparsity. So that's where the bicriteria approximation comes in. And the error is something that is like square root of epsilon plus delta. And we'll see why exactly this term comes up. Okay, so this is the guarantee that we can obtain. Okay, and note that so because of this, the best you can probably set delta is roughly equal to epsilon. Okay, so it doesn't help go beyond that. Okay, so you can think of getting something like an O of square root epsilon error. All right, and we can show that almost exactly the same things can hold for column selection. So if you have non-negative matrices A and B, and if you assume there is some k-sized set S, subset of the columns, such that approximating B using the subset of columns of A has some epsilon error, then you can get an error which is something like this. Okay? And the number of columns we use is this factor more, okay? And it depends on the delta. Right? So these are our results. And so one thing to note here, which is kind of a weakness of our methods, is that this is an additive error guarantee. Okay, so you have this plus delta, square root delta that shows up. So, and this is an additive error guarantee. And in the case when A equals B, when you have the same matrix approximating itself, and when you want columns of a matrix approximating itself, this is weaker than some of the known results for very small epsilon. Okay? So there are relative error bounds known in the case A equals B. So our result is weaker than that. Okay? But one thing to note about additive guarantees is that they are typical in most Frank-Wolf type algorithms. Okay? So given the kind of algorithm we are using, it's no surprise that these kind of additive errors are showing up. And also, this is probably unavoidable for the case A equals B, for the case when A and B are arbitrary. Okay? So because we are trying to approximate columns of B using columns of A, and so even the case when error is 0 is probably NP-hard. We haven't shown it formally, but I think this follows from some known results. Okay? Known results on hardness of sparse recovery in particular. Okay, so this is potentially unavoidable. Okay, but one thing to note is that this algorithm is actually pretty good in practical settings where usually you have a matrix and you know that 90% of its mass can be explained by using a small number of columns and 10% is noise of high rank. Okay, and in this kind of settings, in some sense, most of these earlier multiplicative results don't imply anything, while we actually can get some kind of non-trivial guarantees in this case. Okay, so these are the kind of settings in which we use these algorithms. Okay, so this is a general discussion of the main result. So let me now outline the rest of the talk. So first I'll talk about sparse regression and basically our algorithm for it. And then we'll see how you do column selection using this result for sparse regression. Okay. So what is the setup again? So if you recall, so you want to solve Ax equals B, and you assume that there is a k-sparse x such that the error is less than epsilon times the L1 norm of B. Okay. And what you can assume without loss of generality, of course, is that every column of A has unit norm, okay, a unit L1 norm. Okay. And you can also assume you can set P equals the normalized version of B so that we don't have this ugly term on the right. So now this equation becomes something clean. Okay. So one thing, the moment you write it like this, is that X is almost a convex combination of a few of the columns of A, right? Because the L1 norms all match up, and this is one nice property you get because of non-negativity. Okay. So you get that sum over Ixi is approximately 1. Okay. So why do we care about convex combinations, right? So so before that, so note that in fact you can show that there exists some good convex combination such that sum of alpha I ai is at most 2 epsilon. Okay, with a little bit of loss, you can move from an approximate convex combination to an exact one. Okay, so why do we care about it? And the reason is that, so this is where Frank-Wolf iterations come in. Okay, so what is the Frank-Wolf algorithm? So roughly speaking, it is the following. So it's an iterative algorithm where at every step you maintain some convex combination of the columns. Okay? And at every step, what you do is you add a new column to the mix. Okay? So the algorithm typically looks like this. So you have a potential phi, okay? And you initialize Q to be an arbitrary column in the matrix. And now you iteratively try to move towards a direction that maximizes a certain potential. Okay? Maximizes or minimizes a certain potential. Okay? So I should have written minimizes here. And you update it like this. And what is the idea here? So the idea is that you know that your vector P, that your target vector P, can be written as a convex combination of these columns, right? So you can hope to do some kind of an averaging, and if you average this quantity, then it's like essentially moving to the point 1 minus eta times Q plus eta P, okay, which is like moving from P in the direction of your target. Okay. So this is the idea behind Frank-Wolf iteration that you essentially simulate. Okay. And this is also called coordinate descent. It's very common in machine learning type settings. Okay. And so the guarantees for this algorithm usually depends on the choice of phi and the step size eta. Okay. So the step size is the amount you move along this new vector you add. Okay. And so the difficult thing about the L1 norm is that the obvious candidates for phi don't quite work out. Okay, so one natural choice is you let phi be the distance to your target vector. Okay, so the L1 distance to your target vector, that doesn't work out. And even if you set it to be the KL divergence, this doesn't work out. So the problem with the first one is that it's not smooth enough. The problem with this is usually that it's the usual problem with KL divergence, which is that it's pretty badly behaved at the corners of the simplex. Okay, so that's why this doesn't work out. So what does work out with a little bit of manipulation is a smooth version of KL divergence. Okay, so what we show is if you set phi to be the KL distance between P and this P plus Q by 2, okay, so this is the midpoint between P and Q. So this is, it's 1/2 of what is called a Jensen-Shannon divergence, for those of you who know. So this one, it avoids this problem of being bad at corners, and then you also get a reasonably good guarantee using this. Okay, so that's the main idea, that's the main claim that we will end up proving. Okay. And once you have this choice of phi, the algorithm is very simple. You just do the previous iteration that I mentioned. It turns out setting eta equals something like this works, and you run for so many iterations. Okay. And because you run for only this many iterations, you get the sparsity guarantee that I mentioned. And we just have to show the appropriate error bound. And the main lemma that helps us analyze this, so this is what comes out of carefully choosing this potential phi, which is that as long as your potential is large enough, it's more than some quantity like epsilon plus delta, then the potential always reduces in each iteration. Okay? So this is what we usually would like to show in a Frank-Wolf type algorithm. Okay? So this is the main claim that we show. Okay. And note that once we show this, we are kind of done, because after a certain number of iterations, the fact that the potential drops in every step means that after a certain while, the phi has to drop below epsilon plus delta. Okay, so this is pretty easy to show. Yeah. And once you have this, you can show that by Pinsker's inequality, you can show that you can bound the L1 norm using the KL divergence, and this is what leads to the approximation guarantee. Okay. So this is the idea behind the proof. Okay. So the lemma itself is kind of technical, and so if we could linearize a certain function, then you can do averaging, but it turns out that we can't linearize the particular function we have at hand. Okay. So this leads to this a slightly technical analysis. So we'll have to do an appropriate thresholding and use a proxy for the potential that we are doing. Okay? So I'm not going to go into the details of this because this is, it's technical and I don't think it has too much intuition. Okay? But we can show that this kind of a potential drop happens, and therefore we would be done. Okay? So we have the main result like this. Okay? So in the couple of minutes I want to talk a little bit about column selection and why it's related to, how you relate it to sparse regression. Okay, so the connection is actually very simple. Okay, so recall that in column selection you have two matrices. You want to pick a subset of columns so that you approximate this. Right? So how do we cast this as a sparse regression problem? Okay, so in sparse regression you just have one vector. You have a bunch of columns, you want to approximate it using this. But you can capture it if you allow infinite A's, right? Because you can flatten the whole matrix B into one vector little b. And you think of a whole bunch of columns forming a matrix A prime, where these columns are all flattened versions of this column tensored with some non-zero vector z. Okay, so if you think about it, this actually turns out, you allow all possible z, so which is why you have infinitely many columns. And now column selection can be written as some kind of a sparse regression problem. Okay? And so this is what we show, and essentially now you have an infinite matrix. How do you do it? We show that you can cast the problem of finding a good column in this infinite set of columns as some kind of a linear program. Okay? And this thresholding idea that we had before is kind of key to casting it as a linear program. Okay, so if you just had this log term that we had in the KL divergence thing, then it becomes non-convex, but this thresholding makes it linear. Okay, so that's the main idea behind this, and this is what completes the proof of the main theorem. Okay, so I wanted to just end with a few conclusions. So this is what I presented is, I think, a somewhat novel approach for doing non-negative problems with L1 error. Okay, and also the algorithm for column selection is quite different from typical algorithms for column selection. Okay, so usually for L2 and so on, people use quite different things, like looking at the determinants of the columns or sampling, things like this. Okay, so this is quite different from those kind of algorithms. And so the main kind of open question in this work is the dependence on error, is this trade-off we have between the error and approximation, is it optimal? Okay, and so it turns out that even if the error is actually 0, you need some trade-off, even if everything is non-negative. And this is some reduction from set cover. And but is the dependence optimal? We don't know. Okay, and also there could be more applications. Like one thing I didn't mention is that this result directly implies something about NMF if you have what is called this anchor word assumption. Okay, but if you don't have that assumption, can you come up with like a potentially large B, and do these ideas help? Okay, so that's an interesting open question. Okay, so let me stop there, and thanks for